In this class, we'll talk about the acceleration formula. The prerequisites for learning the acceleration formula is to know about the relative velocity formula, which was covered in section 16.5. So let me motivate this with the prerequisite, which is the relative velocity formula. So we had seen in section 16.5 that VB is velocity of A plus velocity of B with respect to A. Now, in order to find the acceleration, we can differentiate this expression with respect to time to get AB, which is the first derivative of B, is equal to AA plus. Now, when you take the derivative of VB with respect to A, you end up with two components, AB with respect to A tangential and AB with respect to A normal. It turns out that these tangential and normal components are given by alpha cross RB with respect to A plus omega cross RB with respect to A. So please refer to the textbook for a derivation of the formula. In this class, I'm just going to give you an interpretation of how this formula is, how to visualize this formula. So here is how to visualize the formula. So the interpretation is as follows. So A, B, say are 2 points on a rigid body, and say this is the initial position of the body, and then the rigid body goes through a transformation. It could translate, it could rotate, and it ends up in this position, A, B. This is the final position. Now we can actually decompose this motion of the rigid body into two moves. First, it will translate when it translates, it sort of moves itself, but it doesn't change its orientation. And then we can rotate about A. So when we rotate about A, we get the body in its final position. This rotation was achieved because the body rotated with an angular acceleration alpha and angular speed omega. So due to the angular acceleration alpha and speed omega, this particular point B would have AB with respect to A tangential and AB with respect to A normal. Okay, so in other words, we are interested in motion of B. It is simply the sum of motion of A, which is the translational motion, plus the motion due to rotation. In fact, this part is only due to omega. So due to omega, so it's omega cross R, and this part is due to alpha or angular acceleration. It is given by alpha cross R. Okay, so the formula which is used to relate the acceleration between 2 points of a rigid body is given by this, and this is the formula which we'll be using today to solve problems. Okay. So let's get started with a simple problem. Okay, so the question is about a disk which is spinning with a fixed or a constant angular speed 4 radians per second and angular acceleration 2 radians per second without slipping. We have to find the acceleration of a point B, which is shown in the figure. Okay, now you also told that there is no slipping. What it means is that this point here, the contact point, has a velocity of 0. If it was slipping, then that velocity would not be equal to 0. So we are asked to find a b. Okay, now obviously if you want to find ab, let us write the formula which we just learned about. AB is AA plus omega cross r p with respect to a plus alpha cross r p with respect to a. Now it turns out that you can actually simplify this formula for in-plane motion. By that I mean if the body is moving in the plane and angular speed is pointing outwards or inwards, in other words, angular speed is perpendicular to the motion of the to the rigid body, then you can actually simplify this formula to this. Okay, so this is the formula which is which we'll use here. Okay, so this formula requires us to let's see, it requires us to find acceleration of point A, angular speed which is given to us, angular acceleration is given to us, and the length of the vector from A to B. Okay, so what I'm going to do is first I will draw a coordinate axis. So let's say that my coordinate axis is that I points along the motion and j points perpendicular. Okay, now I'm ready to find the acceleration of A. Okay, uh, now the acceleration of A is something we've done previously. This is if we talked about motion of particles, constrained particles, where we had those problems with pulleys, if you remember, where when in order to find the motion of the center of a disk, you need to take the condition that the distance moved by an arc. So this is in the initial position in some time. If this point traces, if this point would move by a certain distance d, or let me call it x, then that x is given by the radius times theta. Okay. So it also happens to be this arc length. This arc length is the arc length covered by the disk in when it moves an angle theta. It also happens to be the distance covered by the center of the circle of the disk. So if x is r theta, then v is the first derivative of that. So let's say this a, this xa is r times theta along I. Xa dot is va is r theta dot I, or in other words r times omega I. And then if you differentiate that again, get AA is equal to r omega dot I, it is r alpha I. Okay, so velocity of acceleration of A is now known to us. So we only need to find RB with respect to A. Okay, now RB with respect to A is the vector from A to B. Okay, so let's see what that is. The vector which goes from A to B. So A is here, B is there. We need to find the vector which connects to. So that is given by the radius of the circle of the disk, and we need to resolve it along the x direction. So this is here in this case given to be 45. So the x component is simply r cosine 45, and the y component is r sine 45 degrees. So RB with respect to A is going to be r cosine 45 degrees along I, but mind you, this is going to point in the direction opposite of I, so it's going to be negative I plus r sine 45j. That's because the y component points along the positive j direction. Okay, when you do the math on this, this comes out to be well, let me just keep it as it is and then simplify it later on. Okay, that's known. Omega, the vector, is in the k direction, but we are only interested in the magnitude, so that is simply 4. And alpha is the angular acceleration is given as 2. Now alpha is acting in the clockwise direction, so if you take your right hand and you curl your fingers along the direction of alpha, you'll see that your thumb points into the plane of the paper, which means that it is along the negative k direction, right? Because if ij is here, then k points outside the plane of the paper, pointing outside, so minus k should point inside. So now we are ready to use this formula to find AB. So AB is equal to AA r alpha I minus 4 square minus r cosine 45 degrees I plus r sine 45 degrees j minus 2k crossed with minus r cosine 45 degrees I plus r sine 45 degrees j. Okay, and I will leave the math for you to figure out, but this is what I get after putting the values: 17.31 I minus 8.49 j. So this is the final answer. Okay, so let's summarize what we did here. Okay, in this problem we were told to find the acceleration of point B, so it was a matter of straightforward application of the formula. So in this formula we realized that we were given angular speed and angular acceleration. We were not given the angular acceleration of A, so in order to find that, we used the no slip condition to figure out the position of A as a function of theta, this one, and then we differentiated twice to get the acceleration. In order to find the vector from A to B, we introduced a coordinate frame ij as shown here, and then used our knowledge of vectors to find our B with respect to A. Once we had that, we put in the formula to find the acceleration of B. Okay, let's do another problem. Okay, so let's read the problem. So this is a mechanism where there are three links. Member AB, which rotates about A, member BC, which rotates about B, and then there's a slider at C. In this case, you're given the angular speed of B, 4 radians per second, and you're given angular acceleration of AB, which is 5 radians per second as shown. You are told to find the velocity and acceleration of the slider block. So we need to find VC and AC. These things are unknown. Okay, so to solve this, let's start from what we actually want to do. We want to find VC, okay, and AC. Okay, so since VC is simpler, let's start with VC. Now, VC is the velocity of C, and there's something about the velocity of C which is we know what direction the slider will be moving. It will actually move along this particular direction. So that's given to be the direction actually is given by this thing here. So what I'm going to do is first fix a coordinate frame. Fix it right here, I, J. And now I'm going to assume that velocity of C is let's assume that VC is in this direction. Okay. This is just an assumption. It may be that VC is actually moving downwards, and we'll see that when you do the math it will come out with the right sign, and then we can interpret accordingly. So VC vector is given by VC magnitude, which I just showed here, the VC, times we need to find the component of VC along the X and Y direction, along the I and J direction. Okay, now what will help us is this thing. So the X component is simply the cosine of theta, as I've shown here. So cosine theta is simply 4 divided by 5i plus sine theta j. This should be j and I, sorry about that. Okay, so the sine theta j is simply 3 divided by 5j. Okay, and the last thing to note is that this direction is in the first quadrant like this, so x and y should both be positive, so these have the positive signs. Actually, we can also write AC in a similar way. We know that acceleration of C should be along this groove. So AC will be AC the magnitude times 4/5 I plus 3/5 J. Okay. So we know the direction, we don't know the magnitude. So how do we go about solving for that? So what we do is, since we know the velocity of C, let's see how the velocity of C is related to velocity of B. So we can invoke the relative velocity formula. Vc is equal to Vb plus Vc with respect to B. This is also given by Vb is, well, it's an unknown here, so we need to find Vb. Now we can actually write a relation between Vb and Va, and the reason I'm doing that is because I know the velocity of A, it is just 0. So using the relative velocity formula between B and A, I can write Vb as Va plus Vp with respect to A plus I keep velocity C with respect to P as it is. Okay, so I know that velocity of A is 0, so I cancel it off. So I'm only left with two things, Vb with respect to A and Vc with respect to B. Now, do I know the velocity of B with respect to A? Well, it is simply omega AB crossed with R B with respect to A. So this is just the formula for the velocity of B with respect to A. Similarly, omega VC with respect to B is omega BC crossed with R C with respect to B. Okay, so let's see if we can write these things down. Omega AB is, okay, so I'm going to write this thing, what I wrote here, omega is actually omega AB. So this is omega AB and this is alpha AB. And this thing here, BC is assumed to move, I'm going to assume it moves counterclockwise. So let's call that omega BC and alpha BC. We might need this later on, so I just going to set it up right now. So omega AB is here, it's 4 radians, and that, as you can see, the arrow points in the counterclockwise direction, which means that the angular velocity is in the positive k direction, crossed with the vector from A to B. So the vector from A all the way to B will point like this. It's given by the length of AB, which is 2, times the unit vector in the direction, so that's J, plus omega BC. So we do not know what omega BC is. So I'm going to assume that omega BC is along K. So again, omega BC is given by the magnitude of omega BC times the unit vector, which is, I've assumed it to be in the positive K direction, times the vector from C to B. Okay, this vector goes from, B to C. So the vector from B all the way to C. Okay, so I need to find the vector from B to C. Can I do that? Well, let's see. If I can, so I'm going to write B and C just because it's clutter on the other figure. So I need to find this vector. I can do that if I know this angle. So let me call that, let's say, alpha. Oh, would be called, better word would be phi, because I used alpha for acceleration. Okay, so I know this length here is 0.5. So 0.5 meters is this, and this height here is given by 2 meters. So it looks like I can figure out what the phi is. Right? So BC, first of all, is going to be, what is BC? It's going to be the x component. So the x component is 0.5, right? That is times I, but note that it is pointing along the negative. If you resolve BC along the I direction, you get negative 0.5. And then there is the y component, which will point this way. So it's going to be minus 2j. Okay, so RB with respect to C is simply that. Okay, so what I'm going to do now next is write expression for VC. VC is this down, so VC is times 4/5 I plus 3/5 J equals 4 times 2 is 8. K cross J is minus I plus omega BC. K cross I is J, so minus 0.5 J. So k cross I is j, so minus 0.5 j for the first component, and then k cross j is minus I, so it's going to be plus 2I. Okay, so once we have this, we have in effect written down the equation which has basically two unknowns, Vc and omega Vc. But we also can find two equations because there is an I component, that's j component. So what the thing to do next is to equate the I components on both sides to themselves. If you do that, what you get is, for on the left side we have 0.8 Vc, on the right side there's minus 8, and then there is plus 2 omega Vc. For the j component, we have 3/5, which is 0.6 Vc, equals, there's nothing for j here, there is minus 0.5 omega Vc. So two equations, two unknowns. If you solve them, you get omega Vc is equal to 3 radians per second, and Vc is minus 2.5 meters per second. So what we got is the velocity of c, it turned out to be negative of what we had assumed it to be, which basically means that we assumed the wrong direction. So it came out to be not this direction, but in this direction. So Vc is pointing that way, pointing down. Okay, now having got that, let's now move on to find the acceleration. So this is, as you see, it's a very similar recipe as this one. So AC is AB minus omega. I'm going to directly write the formula which I wrote, which simplifies omega cross R. So this is relation A, B, and C. So it's going to be omega B, C square, or C with respect to B, plus alpha BC cross RC with respect to B, plus, sorry, that's it. Okay, now in this formula again, we have a term AB, and I don't know what AB is. However, I do know what AA is. It is simply 0. So I'll relate B to A using the relative acceleration formula. So AB is AA minus omega AB square, or B with respect to A, plus alpha AB cross R B with respect to A. So this is just the first term, and then we also have the second one. Okay, so now since we have got this, let's try to write down individual quantities. Okay, AC is, well, what do we know about AC? We know the direction of AC, it's along this line, but we don't know the magnitude. So what I'm going to do is I'm going to take it to be, well, it's already wrote it down here, so I'm going to just write this down. So it's AC 4/5 I plus 3/5 J. Acceleration of A is 0, so that's easy. Acceleration of AB, sorry, the angular speed of AB is given to be, it's 4, so that's going to be 4 square. The vector from A to B, I had written it down earlier. It is, it's right here, it's 2J, plus alpha AB. Alpha AB is 5 radians per second square, but it is in the clockwise direction, which means that it's going to be 5 times minus k crossed with the vector from A to B, that's simply 2j, minus omega bc squared. So omega bc is 3. We found it in the previous calculation, so that's going to be 3 square. The vector from B to C is something we also found out. It's right here. It's going to be minus 0.5i minus 2j plus alpha bc is, well, it's an unknown, just like omega bc was. So I'm going to assume it to be in the counterclockwise direction. So it's alpha bc times k crossed with c from B to C. So it's the same as this 0.5i minus 2j. Okay, so all I have to do now is to simplify this. So AC 4/5 I plus 3/5 J equals uh, uh, 632 minus 32J. 5 times 2 is 10. So 10 K cross J. K cross J is minus I, and that minus multiplies with this minus to give a plus I. So this is going to be plus 10I. Okay, then we have minus, there's a minus here, there are two minuses, so I'm going to put a plus here. That's going to be 9 times 0.5i plus 2j. And finally, there is alpha bck cross 0.5i, so that's going to be 0.5 alpha bck cross I is j. And then k cross j is minus I, so this is going to be plus 2 alpha bc I, because k cross j is minus I. Okay, so when you look at this long expression, you see that it has two unknowns, alpha bc and ac. However, really in this vector equation there are two equations sitting in. One is for the I components and the other is for the j component. So what we'll do is we'll compare the I components. When you compare the I components, you get 0.8 AC is equal to 14.5 plus 2 alpha BC, and when you compare the J, you get minus 0.6 AC, so that's coming from here, equals minus 14 minus 0.5 alpha BC. So two equations, two unknowns, gives me AC is there. A byproduct will be alpha BC. You may or may not solve it for, because we are not asked for it, but comes out to be 12.4 radians per second square. So what we were after in this case was AC, that is minus 13. Just like VC, turns out that AC was in a direction opposite to that of what we had assumed. It is pointing downwards, just like this. So this is this way. Okay, so let's just summarize. So in this particular problem, we were asked to find the acceleration of a point of the slider of this mechanism. We were given the angular speed and accelerations of one of the links. So what we did was we started with what we were after, the acceleration and velocity of C. We wrote down formulas for C in terms of B, and also acceleration for C in terms of B, and then related the acceleration of B to that of A using the same formula. We exploited the fact that the velocity and acceleration of A is 0. We simplified the expressions. We ended up with two equations, two unknowns, by equating the I and j components, and those two equations were solved for the unknowns. So in the first case, for the velocity, we were able to solve for the magnitude of the velocity of C and also the angular speed of BC. In the second case, for the acceleration, we were able to solve for acceleration of C and the angular speed of link BC. Okay, so this is how you solve problems involving acceleration.